Welcome to Night Lesson. Relax and learn along the way. Intro. Gaze into the infinite night sky, an ocean of darkness, studded with the sparkling diamonds of countless stars. Yet, among all this light, there are regions of absolute, impenetrable blackness. A darkness that is not merely the absence of light, but something that actively devours light. A place where the laws of physics as we know them reach their limits, and time itself loses its familiar, steady rhythm. We are accustomed to understanding the universe through the light that reaches us from stars and galaxies after a journey of eons. But perhaps the most fascinating objects are those we cannot see directly. We can only sense them through their immense effect on their surroundings, like an invisible giant making the stars around it dance, bending and distorting their light as if one were looking through an invisible lens. What is today a central part of our understanding of the cosmos was once just a strange mathematical possibility in Albert Einstein's equations of general relativity. An idea so bizarre and radical that even its discoverer long doubted its real existence. A hole in the fabric of reality. Our journey takes us to that very place. From the first abstract, theoretical thoughts, through the fiery birth of these cosmic giants in the hearts of dying stars, to the historic moment when humanity first gazed upon the luminous face of a black hole. Let us now journey together into these silent, dark depths of space. Without rush, without hurry, with only our quiet curiosity and the infinite stillness of the night that surrounds us. Chapter 1. The Thought That Pierced the Night. Our journey into darkness begins not with a glance through a polished telescope, but in the soft glow of a candle in the quiet world of the 18th century. It is a journey that began not in space, but in the mind of a single man. In England, long before humanity even dreamed of leaving the earth, the natural philosopher John Michel sat and pondered the nature of the stars. His tools were not lenses and mirrors, but the elegant laws of gravity that Sir Isaac Newton had gifted to the world. He thought about the concept of escape velocity. Every child who throws a stone into the air knows that it will fall back down. To escape the gravitational pull of a planet like Earth, an object must reach an enormous speed, about 11.2 kilometers per second. A rocket must push against gravity with this force to venture into the cosmos. Michel then posed a simple but profound question. What if a star were so unimaginably massive and compact that its escape velocity exceeded the speed of light? Light, the fastest thing we know, would then be like a stone thrown into the air, only to inevitably fall back down. It could never escape the star's gravitational pull. The star itself would remain invisible to an observer in space, a dark spot on the firmament. He called his visionary idea a dark star, a thought written down on yellowing paper, a sketch that perhaps showed only a black disk in a sea of hand-drawn stars. An inkling that was more than a century ahead of its time. This remarkable idea lay dormant for a long time in the annals of science, until the beginning of the 20th century, when a young patent clerk named Albert Einstein took the stage and turned our entire understanding of the universe upside down. With his general theory of relativity, he explained that gravity is not a mysterious, invisible force acting between two bodies. Rather, it is a fundamental property of space and time itself. Imagine the universe as the calm, mirror-smooth surface of a deep lake, the fabric of spacetime. Every celestial body resting within it creates a dent, a gentle depression in this surface. Our sun pulls the water around it inward, and the Earth orbits like a leaf on this slanted surface. A planet like Jupiter pulls it deeper. Mass, as Einstein taught us, tells spacetime how to curve, and curved spacetime tells mass how to move. Even light must follow these curves. Its path is gently bent near massive objects. This new, poetic, and at the same time mathematically precise description of gravity opened up entirely new possibilities. And it did not take long for someone to recognize the most radical consequences of this theory. Just a few months after the publication of Einstein's equations, in the midst of the turmoil of the First World War, the German physicist and astronomer Karl Schwarzschild found a solution on the Russian front. In the lulls between artillery strikes, he devoted himself to pure mathematics and calculated what would happen if you concentrated an extreme amount of mass into an extremely small point. His calculations revealed something unheard of. If an object is compressed to a certain critical radius, known today as the Schwarzschild radius, the dent in spacetime becomes infinitely deep. It becomes an abyss. Spacetime curves so intensely that it essentially closes in on itself, cutting off a region from the rest of the universe. Nothing, not even light that enters this region, can ever escape. For our Earth, this radius would be a tiny 9 millimeters. If our entire planet were compressed to the size of a marble, it would become such an object. Thus, in the trenches of a global conflict, the first mathematical description of a black hole was born. It did not yet bear this name, but its existence was now a theoretical possibility. A thought that once began in the candlelight had now taken the form of an irrefutable mathematical equation. The stage was set to search for these strange, invisible objects that might be lurking somewhere out there in the silent expanse of the cosmos. Chapter 2: The Death of a Star. In a distant, nameless cradle of swirling gas and luminous dust, a life of immense mass begins. This is not the fate of an ordinary star like our Sun. No, the birth of a black hole requires a true giant, a star that unites at least 20, perhaps 25 times more matter than our home star. Seen from afar, it appears as a brilliant blue point on the velvety firmament, a majestic, pulsating light. Its glow is so intense that it outshines the surrounding stars, a sign of its enormous energy and its extravagant lifestyle. For millions of years, this blue giant lives in a state of calm but immense tension. Its existence is a constant, silent struggle between two fundamental forces of the universe. Deep in its heart, in a core of extreme heat and immeasurable pressure, an act of cosmic alchemy takes place. Atoms of hydrogen, the lightest of all elements, are squeezed together until they fuse into helium. This fusion releases a tremendous amount of energy, a radiation that relentlessly pushes outward, preventing the star from collapsing under its own immense weight. It is a dance that lasts for eons. The outward-pushing heat of fusion, bracing against the relentless, inward-pulling grip of gravity. When the hydrogen in the core is exhausted, the next stage of this alchemical process begins. The star converts helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. With each new stage, the core becomes hotter, denser, and the process accelerates. The life phases that once took millions of years for lighter elements now shorten to millennia, years, and finally, mere days. The star creates within itself the building blocks of life, which will one day travel through the universe and form new worlds. But this chain of creation has an end. It ends with iron. The iron heart of the star is no longer a source of power, but a tomb for energy. Unlike the lighter elements, the fusion of iron does not release energy, it consumes it. The internal furnace that supported the star for millions of years goes out. Suddenly, and without warning, the outward force ceases. For a moment, shorter than the blink of an eye, the universe holds its breath. Gravity, which had been held in check for so long, triumphs. In an unstoppable, cataclysmic act, the iron core collapses in on itself. It implodes at a speed reaching nearly a quarter of the speed of light. The matter is packed so densely that the atoms themselves are crushed. Electrons and protons merge to form neutrons. The matter resists one last time, a principle known as neutron degeneracy pressure, a final, desperate stand against total collapse. In a less massive star, this pressure would halt the collapse, leaving behind a neutron star. But this giant is too massive. Even this final line of defense is breached by the overwhelming force of gravity. As the core continues to collapse, the outer layers of the star, still unaware that the furnace has gone out, crash down upon this newly formed, extremely dense core with tremendous force. They bounce off it as if from an indestructible wall and are catapulted outward by a massive shockwave. What follows is not an ordinary explosion, but the unfolding of a cosmic flower. Viewed from a distance, this happens in a kind of sublime slow motion. One of the most powerful detonations the universe knows, a supernova. Veils of glowing gas, enriched with all the heavy elements the star created in its life, expand majestically and relentlessly into space. They paint a fleeting work of art across the heavens. But while the star's shell becomes a beautiful, expanding nebula, a monument to its former life, the collapse in the center continues. Nothing can stop it now. The core continues to collapse in on itself, becoming denser and denser, until it becomes a point of infinite density, a place where the laws of physics as we know them lose their meaning. In the heart of the dying flower, a void is born, a point of absolute darkness that begins to devour everything around it. Chapter 3: Anatomy of the Abyss. What now remains in the silent center of destruction, after the star has breathed its last light? The answer our theories give us is as simple as it is incomprehensible. In the heart of the darkness lies the singularity. It is the point to which the entire core of the star, the mass of millions of Earths, has collapsed. A point with no extension, no volume, but with a density that stretches to infinity. Here, in this place that is not a place, our familiar laws of physics break down. Space and time, the stage on which our universe plays out, merge into something new, unknown, and lose their usual meaning. Do not try to imagine the singularity as a tiny black ball in space. That would be misleading. It is, rather, a moment in time, an unavoidable destination, an endpoint for everything that crosses its boundary. Like the water of a river flowing unstoppably toward a mighty waterfall, space-time itself flows into the singularity. For every particle, for every ray of light that falls in, it is the future, a future from which there is no escape. But for us as observers from a safe distance, another aspect is far more tangible, an invisible boundary that surrounds this point of the unknown, the event horizon. This is not a physical wall, not a solid surface you could touch. If a spaceship were to cross this threshold, the occupants would initially feel nothing. No jolt, no alarm. The stars ahead would still shine, yet they would have passed the point of no return. The event horizon is the boundary where gravity becomes so powerful that the speed needed to escape exceeds the speed of light. And since nothing can be faster than light, escape has become impossible. Every path, every possible trajectory. In physics, they are called geodesics, that an object can take from here on inevitably leads further inward, deeper into the abyss, toward the singularity. Even if you were to fire your engines at full power and try to fight your way outward, you would in truth only be moving faster toward the center. Inside the event horizon, the direction out has vanished. All paths lead to the same inevitable end. One might think that such an extreme and powerful object must be unimaginably complex. But the opposite is true. Black holes are among the simplest objects in the entire cosmos. While a star like our Sun is made of countless particles, with complex chemical layers, magnetic fields, and solar flares, a black hole can be completely described by just two things: its mass, which is how heavy it is, and its angular momentum, which is how fast it spins on its axis. This principle is so fundamental that it has its own name, the no-hair theorem. The hair, Here is a metaphor for all the additional information an object normally possesses: its shape, its chemical composition, its temperature, its texture. When matter falls into a black hole, whether it's an entire star, a planet, or a cloud of interstellar dust, all these complex details are lost to an outside observer. The black hole does not remember what it was made of. It swallows the information and simply becomes a little more massive or spins a little faster. All the subtleties, the entire history of the matter that fell in, are smoothed out and erased, hidden behind the silent, perfect curtain of the event horizon. What remains is a pure, almost abstract form of gravity, quietly curving the space around it. Chapter 4: The Dance with Time. How does time feel when it stretches and curves like a lazy river? Near a black hole, time ceases to be a constant timekeeper, a metronome that keeps the universe in a steady rhythm. Instead, it becomes a malleable substance, influenced and shaped by the immense mass that distorts space. Imagine a journey undertaken by a friend, equipped only with a simple clock. As you remain at a safe distance, watching their ship approach the invisible edge, something strange happens. You look at your own clock. Its hands move with their usual precision. But when you look through your telescope, you see the second hand on your friend's clock begin to hesitate. Each tick lasts longer than the one before. Their movements on board the ship become infinitely slow, as if they were moving through invisible, thick honey. They raise a hand, and the gesture that should take a moment stretches over minutes, then hours of your life. The closer they get to the event horizon, the slower their time appears to flow. The light that reaches you from their ship loses energy on its journey out of the deep gravitational well. It is stretched, its wavelength shifting ever further into the red spectrum. What once shone brightly becomes a deep, dull red, then infrared, and finally fades completely from your visible range. To you, your friend seems to be frozen forever at the threshold of the abyss, a final, fading image that never quite disappears, but stretches into eternity until it is indistinguishable from the cosmic background radiation. You will never see them cross the event horizon. Their final moment will, for you, last forever. For the traveler, however, the experience is entirely different. Inside their spaceship, their clock ticks normally. Every beat of their heart feels the same. Every thought flows at its usual speed. For them, there is no moment of freezing. They feel nothing of the time dilation you are observing. But when they look back out their window, at you and the rest of the universe, a breathtaking spectacle unfolds. They see the stars race across the sky like streaks of light. They see galaxies age and change in a cosmic time-lapse. In the few moments that pass for them as they fall toward the event horizon, millennia, perhaps even millions of years, could pass outside. They become a witness to the distant future of the universe, compressed into a brief, personal instant. But gravity not only shapes time, it also shapes matter itself. As the traveler falls, another, relentless force acts upon them, the tidal force. The difference in gravitational pull between their head and their feet becomes more and more extreme. The point of their body closest to the black hole is pulled infinitely more strongly than the point farthest away. This unequal pull tugs at them. For a smaller, stellar mass black hole, this happens long before the event horizon. Their body would be slowly and inevitably stretched, atom by atom, until it becomes a thin stream of matter flowing into the singularity, a process that astronomers call, with an almost poetic sobriety, spaghettification. For a supermassive black hole at the heart of a galaxy, however, the event horizon is so vast that the curvature of space at this boundary is much gentler. The tidal forces there are comparatively weak. A traveler could cross this point of no return without being immediately stretched. They would simply glide through, unaware that they have crossed a threshold beyond which space itself is falling toward the center faster than light can escape. Their fate would be sealed, But the moment of transition itself could be one of eerie silence, a quiet fall into the heart of darkness, where space and time lose their familiar meaning. Chapter 5. The Giants in the Hearts of Galaxies. The abysses born from the collapse of individual suns are merely the harbingers of a far more colossal presence. Their silence is the silence of a single fallen flower in an immeasurable forest. Astronomers, peering deep into the centers of distant islands of stars, discovered that there, in the heart of almost every large galaxy, lurks a completely different kind of giant. A being of unimaginable mass, not born from the death of a single star, but through processes spanning eons. These are the supermassive black holes, the silent rulers of billions of suns. Our own home, the Milky Way, also holds such a secret at its center. About 26,000 light-years from Earth, hidden behind dense clouds of interstellar dust and gas, lies an object called Sagittarius A star. It is invisible, a patch of pure absence in the brightest, densest part of our galaxy. Yet its existence is as certain as the sun in our sky. We feel its presence not by its light, but by its influence, by the cosmic dance it conducts. For decades, telescopes have fixed their gaze on this heart of darkness. They have not tracked the black hole itself, but a handful of stars in its immediate vicinity. These stars, trapped in an invisible gravitational well, perform a breathtaking ballet. They move in tight, elliptical orbits at dizzying speeds around an empty point in space. Their movements, recorded over years and decades, paint luminous trails in the darkness, like cosmic fairy lights swinging around an unseen anchor. Using the ancient, venerable Kepler's laws, which once explained the motion of planets in our solar system, astronomers were able to weigh the mass of this central object. The result was unequivocal. There, at the center, must be a mass of about 4 million suns, compressed into a tiny volume. Sagittarius A star is a relatively quiet giant, mostly slumbering in obscurity. But the universe knows far more formidable beasts. Let us look 55 million light-years away, to the giant elliptical galaxy Messier 87, or M87 for short. In its course, it's a true behemoth. Its mass exceeds that of our Sun by 6.5 billion times. This giant does not sleep. It is an active engine that shapes the destiny of its entire galaxy. Around it swirls a vast accretion disk, a luminous whirlpool of gas, dust, and the remnants of torn-apart stars. Through unimaginable frictional forces, the material in this disk is heated to millions of degrees, until it shines brighter than all the stars in the galaxy combined. From the heart of this glowing maelstrom erupts one of the most spectacular phenomena in the cosmos, a colossal beam of high-energy particles, a so-called relativistic jet. Driven by extreme magnetic fields, which are twisted and amplified in the rotating matter around the black hole, a portion of the infalling material is bundled and launched thousands of light-years into space at nearly the speed of light. It is as if the black hole, this ultimate abyss, spews a part of its meal back into the universe in a blinding jet of energy. This jet is a cosmic signature, a visible sign of the untamed power at work in the hidden center of M87. These galactic hearts are more than just endpoints for matter. They are the gravitational anchors around which entire worlds of stars form and revolve. Their existence confronts us with the deepest questions about the origin and evolution of the universe. How did they become so immeasurably large? And what role do they play in the grand cosmic cycle that creates new suns and worlds from stardust? Their silent, immense presence is a whisper from the deepest reaches of time, a reminder of the fundamental forces that hold the fabric of the cosmos together. Chapter 6. A soft whisper from the void. For a long time, the existence of a black hole seemed absolute, a point of no return, a final state of matter. Once born from the fire of a dying star, it was believed they could only grow, insatiably consuming everything that crossed their path, but never getting smaller. They were the eternal archives of the cosmos, the silent endpoints of stellar destinies. But in the 1970s, a brilliant mind named Stephen Hawking listened to the universe in a new way. He connected the immense world of gravity, described by the general theory of relativity, with the fleeting, strange world of quantum mechanics. And from this union came an insight that would forever change the image of these dark giants. Black holes are not completely black, and they are not eternal. They radiate. This glow is not a fire as we know it. It is an infinitely more subtle, colder glimmer that arises from the fundamental laws of space itself. Quantum field theory teaches us that what we perceive as an empty vacuum is, in truth, a simmering ocean of possibilities. On the smallest scales, pairs of so-called virtual particles, a particle and its counterpart, the antiparticle, are constantly popping into and out of existence. They flash into being for an unimaginably brief moment, only to annihilate each other in the next instant. A cosmic breath happening in secret. But what happens when this fleeting event occurs right at the edge of a black hole, at the invisible boundary of the event horizon? Imagine this boundary, a cascade of space-time plunging relentlessly inward. If a particle pair is created there, fate can separate the two partners. One particle is caught by the immense gravitational pull and falls beyond the horizon into the singularity. Its partner, however, which came into being just outside this boundary, can escape. It flees into empty space, a tiny flash of light that seems to come from nowhere. To an observer far away, it looks as if the black hole has emitted this particle. This faint, steady emission is Hawking radiation. To exist, the escaping particle must have energy. It borrows this energy from the immense gravitational field of the black hole itself. According to Einstein's famous connection between energy and mass, E equals mc squared, even the smallest loss of energy is also a loss of mass. Thus, with each escaping particle, the black hole becomes a tiny, imperceptibly small bit lighter. It is evaporating. This process is of an unimaginable slowness. A black hole with the mass of our Sun would take a period of time to completely evaporate that exceeds the current age of the universe by many orders of magnitude. It is a process that stretches over trillions and quadrillions of years, a soft whisper that will only come to an end in the deepest future of the cosmos. But this slow decay holds a deep, unsettling puzzle, known as the information paradox. Hawking radiation is purely thermal. This means it is random and chaotic, like the faint glow of hot embers. It carries no ordered information within it. But what about all the information that has fallen into the black hole over the eons? The precise arrangement of a star's atoms, the complex structure of an entire galaxy it might have swallowed. All of this is information. Think of all the information that falls into the abyss as luminous, infinitely complex patterns. Quantum mechanics, however, has an unshakable law. Information can never be destroyed in the universe. It can be transformed, rearranged, but it cannot be erased. If the black hole now slowly evaporates, leaving behind only a cloud of simple, structureless heat radiation, where has all the information gone? Is the story of the star, its composition, its temperature, its entire being, wiped from the cosmos forever? This would be a violation of the most fundamental principles of the quantum world. Here, the two great pillars of modern physics, relativity and quantum mechanics, collide. This paradox, this soft whisper from the void, is perhaps not a contradiction, but a signpost. It points to a deeper level of reality that we do not yet understand. A level where information might not be lost after all, but is subtly encoded in the outgoing radiation, or is released in some unknown way during the final moments of evaporation. The slow death of black holes is thus not just an end, but also a beginning. The beginning of a search for a new physics that can reconcile the largest with the smallest. Chapter 7. The Echo of Spacetime. Since the dawn of our curiosity, we have perceived the cosmos with our eyes. First, with just a naked eye glance at the starry sky, then through the lenses of ever larger telescopes, which collected light from the deepest corners of time. Light in all its forms, from radio waves to gamma rays, was our only connection to the universe. But what if there were another way to perceive the cosmos? What if we could not only watch it, but also listen to it? This question is rooted in a thought from Einstein, one of the most profound consequences of his theory of relativity. He predicted that the fabric of the universe, space-time itself, is not rigid. It is dynamic, like the surface of a placid lake. And when massive objects are accelerated in this lake, for example, two black holes dancing around each other in an ever-tightening spiral, they create ripples. Not ripples of light or matter, but ripples in the fabric of reality itself. Gravitational waves, which spread out in all directions at the speed of light, an echo of the most tremendous events in the cosmos. But this echo is unimaginably faint. When such a wave, sent out by a cosmic catastrophe billions of years ago, passes through the Earth, its effect is minuscule. It stretches and compresses the space it travels through by an amount smaller than the diameter of a single atomic nucleus. For decades, detecting these waves seemed an unattainable dream, a theoretical curiosity that would forever remain hidden in the noise of the universe. But humanity did not give up. Driven by the desire to open this new window to the cosmos, an instrument of unheard-of precision was conceived and built. LIGO, the Laser Interferometer Gravitational Wave Observatory. In two widely separated locations in the United States, two identical, L-shaped detectors were constructed. Each arm of this L is a 4-kilometer-long tunnel, in which a near-perfect vacuum is maintained. In these tunnels, a highly stable laser beam is split and sent on a journey back and forth. At the end, the two light beams are brought back together. The principle is of a captivating elegance. As long as everything is perfectly still, the paths the two laser beams travel are exactly the same length. When they meet again, their light waves cancel each other out through interference. There is darkness at the detector. But when a gravitational wave passes through the Earth, something magical happens. It compresses one arm of the detector for a tiny instant while stretching the other. The light beams now travel infinitesimally different distances. Their waves are no longer perfectly in sync. When they reunite, they no longer cancel each other out completely. A tiny, flickering light signal appears, the proof that space-time itself has trembled. And on September 14, 2015, after decades of preparation and waiting, it trembled. Both detectors, thousands of kilometers apart, recorded a signal at the exact same time. It was not random noise. It was a clear, unmistakable pattern. A short, rising chirp, a sound that increased in frequency and volume within fractions of a second before abruptly falling silent. Scientists decoded the message of this cosmic echo. It was the sound of the final moments of two black holes that had merged 1.3 billion years ago, one with 29 times, the other with 36 times the mass of our Sun. In their final death spiral, they orbited each other hundreds of times per second until they merged into a single, larger black hole. In that moment, the mass of about 3 suns was converted not into light or heat, but directly into the pure energy of gravitational waves. For a brief instant, the most energetic known source in the observable universe, and yet completely invisible, an echo in space-time alone. This moment changed everything. We had not only proven Einstein right, we had founded an entirely new kind of astronomy. We could now listen to the darkest, most violent, and previously invisible events in the universe. The slow evaporation of black holes was a prediction for the distant end of time. But this echo was a sound from the present of the cosmos, proof of its ongoing, dramatic vitality, now revealed to our new senses. Chapter 8. The Face of the Invisible. We could feel their effect, calculate their gravity on the orbits of entire star systems. We had learned to listen to their echoes, the subtle vibrations of space-time emanating from their violent collisions. But one question remained, a deep, human desire. Could we ever see one? A black hole itself, by definition, emits no light, not a single spark that could reach our telescopes. It is the perfect absence of light. Yet the theory that had already predicted so many of its secrets whispered of a possibility. One might not see the object itself, but perhaps its shadow, a dark, sharply defined silhouette against the glowing backdrop of matter swirling in a final, desperate dance around the event horizon. The challenge, however, was unimaginable. Even the most massive supermassive black hole in our galactic neighborhood, the behemoth at the heart of the galaxy Messier 87, that same supermassive black hole we have already met, appears smaller from Earth than a small donut placed on the surface of the moon. No single telescope, no matter how large, how precise, or how high it stood on a mountain, possessed the sharpness needed to resolve such a detail. It seemed as if the universe would forever hide its greatest secret behind a veil of blurriness. The solution that was conceived was as poetic as it was brilliant. If no single telescope was large enough, then one would have to build a telescope the size of an entire planet. This was the birth of the Event Horizon Telescope, or EHT for short. It was not a single instrument, but a global orchestra of radio telescopes scattered across the world. From the volcanic peaks of Hawaii to the arid Atacama Desert in Chile, from the mountains of Spain to the icy expanses of Antarctica, 8 observatories aimed their dishes at the same tiny point in the sky at the same time. Through a complex technique called very long baseline interferometry, their signals were synchronized and digitally woven together. In the heart of supercomputers, they merged to form a single, virtual eye the size of the Earth itself. Over several clear nights in April 2017, this planetary eye listened to the heart of M87. The amount of data collected was staggering, so vast that the global internet could not have handled it. Instead, the information was written onto hundreds of hard drives. These silent carriers of the greatest cosmic secret were carefully packed and physically flown to central processing centers. A long, quiet period of patience followed. For 2 years, scientists and algorithms worked to calibrate the petabytes of data, remove the noise from the atmosphere, and merge the signals from the individual telescopes into a coherent whole. And then, on April 10, 2019, the world held its breath. The image was revealed. There it was. Not an abstract diagram, not a simulation, but a real photograph. A luminous, asymmetrical ring of fiery orange and deep red, enclosing a perfect, dark void at its center. It was the shadow of the black hole. It was the face of the invisible. The glowing ring was not the accretion disk itself, but something even more wondrous, the photon ring. It was the light from gas and stars behind the black hole, its path so severely curved by the extreme gravity that it was bent around the abyss before embarking on its long journey to us. Some of these particles of light had even orbited the black hole several times, trapped in a final, unstable orbit before they escaped. The ring was brighter on one side, a more intense glow. This was not a flaw. It was proof of its rotation. The matter swirling toward us on that side experienced a relativistic effect known as Doppler beaming, which made its light appear brighter to us. It was the exact image that Einstein's equations had predicted over a century ago. After all that time of pure theory, mathematical abstraction, and indirect evidence, humanity was looking directly at the edge of the abyss for the first time. It was not an image of terror, but one of deep, fundamental beauty. A silent, fiery circle, marking the boundary between our known universe and the eternal unknown. Outro, the face of the abyss. Our journey tonight began with a whisper, an idea sketched in the mathematics of gravity. For centuries, the black hole was a ghost in the machine of physics, a theoretical curiosity born from the mind of Einstein and others. We followed the clues, the wobble of distant stars, the echoes of colliding giants rippling through spacetime. And then, after so long, we finally saw it. A ring of light framing a perfect circle of darkness, the silhouette of the supermassive heart of a galaxy, captured for all of humanity to see. The imagined became real. These silent giants teach us about the fundamental nature of our reality. They are the ultimate expression of gravity, where the fabric of space-time itself gives way. In their presence, time slows, space bends, and the familiar rules of our world are stretched to their absolute limits. They are a testament to the universe's ability to create structures of profound simplicity and unimaginable density, reminding us that the deepest truths are often found where our understanding meets the edge of the unknown. And yet, for all we have learned, the greatest wonders remain. What lies at the heart of the singularity, where our physics falls silent? What becomes of the light and information that crosses the event horizon, seemingly lost forever? These are not problems to be solved before you sleep, but gentle questions to hold in your thoughts. They are invitations from the cosmos to wonder, to dream, and to appreciate the vast, beautiful mystery in which we all exist. Just as a star collapses under its own weight, you can now let the weight of the day collapse and release. Let go of all your thoughts, letting them drift past the event horizon of your awareness into a quiet darkness. There is nothing left to do, nothing to understand. Allow the gentle, steady pull of slumber to draw you in. The universe will continue its silent, cosmic dance while you rest. And now, drift peacefully into the deep, restorative quiet of the night.
That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.